Okay, very good day. Today we will continue with chapter 2, part 2 on electromagnetism. Okay, in this lecture, we will be covering few subtopics. Okay, the first content will be on the magnetic field intensity H and flux density B, so which is very common in electromagnetism. Then we will be seeing on Faraday's law of electromagnetic induction, and then voltage and force in conductor, and finally we will conclude our lecture today with eddy current. Okay, so what is magnetic flux density? So usually magnetic flux density we will denote with the capital B, and magnetic field intensity with H. Okay, from the name itself we can understand so the function of these terms. Okay, so whenever a magnetic flux, okay, so this is the symbol for magnetic flux, exists in a body or component. It is due to the presence of the magnetic field intensity. So magnetic field intensity is actually uh, how strong the magnetic field is, okay, in the particular body, so which is acting on the particular body. So the resulting magnetic flux density is given by, so this is the formula for the B field, we call it as B field. So B equals to, so phi over A. Okay, phi is the flux in the component. So how many number of lines in the magnetic field? So that is what we are interested, and the area which is covered by the magnetic field intensity. And for the H, the formula is H equals to U over I. Okay, so this is for the intensity. So earlier for the density. So H is the magnetic field intensity in A over M. So U is the magnetomotive force acting on the component. So how much magnetic force acting on that particular component, and L is the length of the component. Okay, so we can see the relationship of B field and also H field in the BH curve. So this is the example of a BH curve that we can see in the real life. Okay, so BH curve of a vacuum. Okay, so BH curve also act in a vacuum, but in vacuum, so it will be slightly different because there are no gravitational influence acting on the body. Okay, so in vacuum, the magnetic flux density B is directly proportional to the magnetic flux intensity H. Okay, so we will use this formula if the question mentioning it is acting on the vacuum. So we straight away use this formula, B equals to mu naught H. So mu naught is magnetic constant. So we can see behind the calculator. Okay, so we can see this constant. Okay, so the constant value is 4 pi times 10 to the power of 97. Okay, so we can use this formula. Here we can see here. Okay, the BH curve in vacuum is a straight line. We start from zero, so it is a very steady state. So later we will see for the other magnetic materials. So the curve will be a bit curved, a bit curved, not a linear curve. So non-magnetic materials such as copper, paper, rubber, and FBH curve almost identical to that of vacuum. So there are some materials which possess almost a linear curve, a similar like in vacuum. Yeah, so we see the BH curve of a magnetic material. So some of the materials that we commonly use are in gravity. So on this world, so we usually these materials experiencing some influence from the gravity. So in the material, the magnetic flux density B depends upon the magnetic flux intensity H. So similar formula. So B equals so earlier B equals to mu naught H. So now we expand it. So we need to times with the relative permeability of the material. So each material it has its own relative permeability for the particular material. So it depends on the question. So if the question is mentioning that we are using a certain material, so we need to get the value of the relative permeability which need to be included in the calculation. So mu naught mu t, so which is the relative permeability of the material, is not constant. Okay, so this is not constant. Nu naught is is a constant. Okay, but nu t is depends on the material, so it's not a constant. Okay, but we can find the value using this. Okay, nu t is 800,000 times b over h. Okay, so the value of b over value of h you times with 800,000. Okay, then you can find the value of nu t. Okay, so we can see this figure shows the saturation curve of three material. So it will start from zero. It will rise rapidly for different materials. So you can see we compare three materials. So it will rise from zero until it reaches steady state. Okay. Okay, we will see one example. So, referring to the saturation curve, so this is the saturation curve we have seen earlier. Determine the permeability of silicon ion. Okay, silicon ion 1%. Uh, so silicon ion 1% is on the top curve. Okay, we want to find the permeability of the silicon ion at flux density 1.4 T. Okay, so this is the flux density and this is the flux intensity. So we want to find at flux density 1.4. So we find 1.4. So 1.4 for this curve, the value at 1.4 is 1000 A over M. Okay, so that is the value. So now we can replace it in the solution. Okay, in the formula. So referring to the graph, the flux density of 1.4 Tesla requires a magnetic field intensity of 1000. So this is from the graph. Okay, so based on this, so we can replace it in this formula we have seen earlier. So nu t equals to 800,000. So B over H. So B is 1.4 given in the question over 1000. Okay, so mu t is 1120. Okay, so this is the value for the permeability, relative permeability of the material, particularly for the silicon ion. Okay, so the value for cast steel and cast iron or the other materials, it will be different. It will be different. Okay, so we need to understand. So let's say we want to find for 0.6. Uh, so the value is 3000. So we need to replace it accordingly. Okay, so we'll move on to the next subtopic. So Faraday's law of electromagnetic induction. So Faraday, as we all know, is the greatest scientist. So in 1831, so Michael Faraday, so he introduced many discoveries related to electromagnetism. So he is one of the top scientists who are really influential in the electrical machine and also power system. Okay, so now known as the Faraday's law of electromagnetic induction. So this is a law that we will use. So it reveals the fundamental relationship between the voltage and flux in a circuit. Because when we are dealing with electricity, so electricity it is having connection with the magnetic. Okay, so when electricity combined with magnetic, it will generate a electromagnetic induction. Okay, which will be useful for us to use any machine continuously. So if not, we like DC, we give power. So as long as the power, it will be operating. So it will not generate anything. So once we cut the power, it will be not functioning. So that is for direct current. But for us to have a continuous supply, so we are using an alternating current AC. Okay, so this electromagnetic induction is something which is very important in electrical generation. So Faraday's law states that if a flux is linking a loop or turn varies as a function of time, the voltage is induced between the terminal. So meaning, so there's a terminal here with a coil. Okay, so if you put a magnet in between, so we cut the electrical current. So we will see a new voltage is induced between its terminal. So this voltage can be used to power some. Okay, so it's very important. So the value of the induced voltage is proportional to the rate of change of flux. Okay, so inside here we have flux. So the more it change, the more electric voltage will be induced. Okay, so that is the discovery that done by Michael Faraday. Okay, by definition, if the flux inside the loop varies at the rate of 1 Weber per second, okay, a voltage of 1 volt is induced between its terminals. So, consequently, if the flux varies inside a coil of N turn, the voltage induced is given by, so the voltage induced is E equals to N. So N is the number of turns. Okay, how many turns in the coil? Okay, and changes in pi is the changes in the flux. Okay, due to the movement, so the cutting of the magnetic magnet. Okay, and uh, changes in t is the time interval. Okay, so usually in second. So Faraday's law established the basis of operation of transformer, generators, and alternating current motors. So imagine the world without transformers, without the electrical generator, and also alternating current. So we will not have the electricity at the first place, and we cannot talk like this. So all the electrical appliances, laptops, phone, everything will be affected. So Faraday's law of electromagnetic induction is very important. Important because it give life to the transformers, generators, and also alternating current motors. Okay, we will see one example. Yes, example 2. So a coil of 2000 turns surround a flux of 5 milliweber, okay, produced by a permanent magnet. The magnet is suddenly withdrawn, causing the flux inside the coil to drop uniformly to 2 milliweber in 1 over 10 seconds. So determine the voltage induced. So we want to find the voltage induced. So when the magnet is inside, so the flux will change more. Flux will be uh, produced, okay, more. But once you move out the magnet, so we can see a drop. Okay, so we want to find the value. Okay, the flux change is so this is flux change. So 5 milliweber minus 2 milliweber, so 3 milliweber. Okay, time changes in time is 1 over 10. So we replace in this formula. E equals to n. So changes in pi over changes in time. So n is given in the question. Okay, so n is 2000. So 2000 times. So this is in milli. So 3 milliweber. So we change it to Weber. Okay, so if we change to Weber, so divide by 1000. So we get 0.003 Weber. So 1 over 10 is 0.1 second. Okay, so once you solve it, so we can see the induced induced voltage. Induced voltage is 60 volt. Okay, so we go to the next subtopic. So voltage and force in conductor. So whenever a conductor cuts a magnetic field, okay, so there's a magnetic field here, okay, generated between the conductor. A voltage is induced across the terminal. Okay, so we put a metal rod in between the conductors. Okay, the value of the induced voltage is E equals to LV. Okay, so BLV. Okay, so what is B? B is the flux density. I is the active length, okay, length of the conductor. Okay, and V is the speed of conductor. Okay, we will see one example for this. The stationary conductor of a large generator have an active length of 2 meters. Okay, so 2 meters here. Okay, and are cut by a field of zero point 0.6. So the value of B is given 0.6 Tesla. So moving at the speed of 100 meter per second. So this is V. So we want to find the voltage induced. Okay, so all the components are there. So this is the solution. E equals to BLV. So B is 0.6, L is 2 meters, and V is 100 meter per second. So if we solve it, we get 120 voltage. Okay, Lorentz force in the conductor. Okay, what is Lorentz force? So when a current carrying conductor is placed in a magnetic field, it is subjected to a force which is called electromagnetic force. Okay, so we have a current carrying conductor. We keep it in the magnetic field. It will be a tool to generate electromagnetic force. Okay, so electromagnetic force also we call it as a Lorentz force. Okay, so maybe we Lorentz he, he discovered the electromagnetic force, so they put name as Lorentz force. The force constitutes the basic of operation of motor, of generator, and many electrical equipment. So because of this force, so when we investigate, so we can utilize this force to power our appliances and machines. Okay, the magnitude of the force depends upon the orientation of the conductor with respect to the direction of field. So the way we keep the conductor, okay, okay, the angle of the conductor is very important because we want to utilize it to we want to get the maximum electricity to be generated or to be produced. So the orientation of the conductor is very important. You will see. So this is the magnet, so north pole and south pole of the magnet. So when we put it perpendicular, so we know, yeah, the magnet, it, it will move from north to south. So the magnetic flux will be like this. Okay. When we put a conductor perpendicular 90 degrees, So 90 degrees to this magnetic field. So we will get the greatest force. Okay, we will get the greatest force when the angle is 90 degrees, because the formula we will times with sine angle. Okay, so this angle. Okay, so sine 90 is 1. So when we use sine 90, we will times with 1. So if that's an angle, so the value might be reduced, maybe zero point 0.6 or 0.7. Okay, and when the conductor is placed parallel, so with the line, on the line of the magnetic field, so magnetic field is moving this way. The conductor also we keep it parallel to the line. Then the angle is we consider as zero. Okay, so sine 0 is 0, so the force will become 0. Okay, so the way we keep the material in between, the conductor in between is very important. Okay, so the maximum force acting on the straight conductor is F equals to B I L. So B is the B field, so L is the active length, and I is the current of the conductor. So we'll see one example. A conductor 3 meter long carrying a current of 200 ampere is placed in a magnetic field whose density is 0.5 Tesla. Okay, so determine the force on the conductor if it is perpendicular to the line of force. So, like in this question, it already say perpendicular. So, when it's perpendicular, so meaning you can induce the voltage or current. Okay, so we want to determine the force. So, we use this formula F equals to BIL. Okay, so B is 0.5. So I is 3 meters and L is 200 ampere. Okay, when we solve it, we get 300 Newton. Okay, so direction of the force acting on a straight conductor. So we'll see this for a while. Okay, so when the magnet is this way, so it will move from north to south. Okay, so it will move from north to south when we place a conductor in between the field. Okay, so it will generate its own magnetic flux. Okay, so it will have its own magnetic flux. So this magnet already have its own magnetic flux, and when we put a conductor, it has its own. So what will happen if it will combine with the other field to form a resulting magnetic field? Okay, so it will become like this. So the one that parallel, it will become strong. So the one that is against, it will cancel each other, and the one which is opposite, so we can see here opposite. So it will be in clockwise, so it will cancel each other, so it will move downwards. Okay, so this symbol, whether uh, this magnetic field for the conductor to be clockwise or anti-clockwise, is determined uh, by by an arrow. Okay, so I always remember this to see whether the symbol of the conductor is X or plus, or is a dot. Okay, so I will show you in the next slide. Okay, so in this case, how we want to determine the direction of the magnetic field. So I will use an arrow. How to use this arrow method? So when we see this arrow from in front, okay, so this will be the front part. Uh, so we will see the view like this. Okay, so in between, uh, in the middle is the needle, so the sharp needle. So if we see from on top, we are seeing this arrow, this dot. So we will see like this. So when we see like this, we understand that the current is leaving the field, is coming out towards you, because we can see from in front. So the arrow is coming towards you. So meaning the current is leaving the field. So when the current is leaving the field, we can use our right hand. So our thumb is the direction of the current, and we just curl our hand. Okay, the other four fingers. So we, if the current is leaving the field, so the magnetic field, the flux will be uh, counterclockwise. Okay, so you can test. If the current entering a field, so the symbol will be X or plus. So like this. Okay, so like this. So if we see here, it's like X, it's like plus. As long there's a cross, okay, as long there's a plus sign, okay. So it means we are looking at this dot from the behind. Okay, so we can see it's like a plus or X. Okay, we can see the dot from behind, so we always can remember. So in this case, so we know the the current is moving inward. The current is entering the field. So you take your right hand, you put the thumb in the direction of the current, and you curl your hand. Then we can get the magnetic field of the conductor in a clockwise. So then we can do our analysis. So this is just for you to understand. Okay, so residual flux density and coercive force. So that's another thing that we call as a residual flux density and coercive force. Okay, so in an electrical machine, so usually a coil will be like this. It will be connected to the current source, and you can see some some wires. Okay, so it will be in a ring shape. So it will be in a ring shape. So we can see it will, all the wires will be around the ring. Okay, so when the current force is given, so it will increase from zero. It will gradually increase. So when the current increase, uh, the value of H and B also will increase. Okay, so we can see the increase start from here. So the increase trace out curve as OA. So it will start from zero in the middle. It will go up to A. So it will slowly increase. Okay, so it will slowly increase. Okay, the flux density reaches the value Bm. Okay, so at this point, so this is Bm. Okay, for the magnetic field intensity Hn. Okay, so if the current is gradually reduced to zero, okay, so slowly you reduce your current, the flux density B does not follow the original curve. So earlier we increase the current, so it enters here until the maximum here. So suppose when we remove the current, it must follow the same pattern, but it will not happen in electromagnetism. So when the current is gradually reduced, so what it will not follow the original curve, but it will move along a curve AB. So it will be like this. So it will move from here to this point. So it will not follow the same line. Okay, we can see it's supposed to reach here, but it is here. This phenomena we call it as a hysteresis. The hysteresis is a memory of a magnetism. It's a process. Okay, so there are two things that we need to understand. Hysteresis is a process. Residual induction is the magnitude, the value of something. Okay, so hysteresis is actually a memory of magnetism because earlier you already put a conductor in a magnetic field. So after over time, uh, the conducting material it will be energized and it will carry its own magnetism. Okay, that's why when you keep new a new metal with a magnet, after some time we can see the new material also can attract uh, uh, some of some of the ions or anything that can attracted by the magnet. Even though the strength is not similar like the real magnet, but it will have the ability to attract. So that is because of this hysteresis. So this is hysteresis is actually a memory of magnetism. So earlier you already magnetized the material, it it will have understanding that it can attract a material, other material, so it will hold the memory of the magnetism for some time. Okay, over time it will goes off, but during that time it will have a memory. So that is what we call it as a hysteresis. Okay, so you can say subsequently when h is reduced to zero. Okay, so h is reduced to zero, the substantial flux density remain. Okay, so this is remain. It is called residual flux density or residual induction BR. Okay, so this is the residual induction. What is residual induction? This is amount of the memory. So earlier we know there's a memory. Okay, so memory. So residual induction is the amount of the memory. Okay, so this is a magnitude. Earlier hysteresis is a process. Okay, so to eliminate the residual flux, it needs to have reverse the current. Okay, well, we need to reverse the current. Okay, in the coil and gradually increase the H. Okay, in the opposite direction. So earlier you increase the H like this. Now you are increasing in the opposite direction. So after some time, we can see this curve will go down until it reaches zero. Okay. So it's supposed to follow here and reach zero, but no, it goes until here. So we further push it to reach zero. Okay, so the magnetic domain gradually change their property orientation until the flux density becomes zero at point C. Okay, at this point, so the magnitude flux density required to reduce the flux is called coercive force. Okay, so this is the coercive force that we want to find. Okay, so the value here is the coercive force required to reduce the flux to zero. Okay, so the final topic is hysteresis loop and also losses. Okay, so transformer and most electric motors operate on AC. The flux in the iron changes continuously, both in value and direction. Okay, so the flux, as we know, it starts from um, plus BM. So from here, okay, so it only considering the hysteresis. So we have seen it move from here to here. Okay, so plus Bm move to plus Br, then it moved to 0, then it moved to negative Bm, then it goes up to negative Br, then move to 0, then move back to plus Bm. Okay, so as mentioned here in the sequence, so we also can relate it with A, B, C, D, E, F, and E again. Okay, so the magnetic materials absorb energy during the cycle, and the energy is dissipated as heat. So when it's positive, it will be absorbed, and when it is negative, it will dissipate as heat. So the amount of heat released per cycle is equal to the area of the hysteresis loop. So when we calculate the area inside here, so it's actually the amount of heat released or gain in the system. Okay, so the eddy current. So consider an AC flux pi that link a rectangular shape conductor. So let's say the conductor in a rectangle shape, so arranged like this, no physical contact. Okay, so according to Faraday's law, an AC voltage E1 is induced across the terminal. So E1 will be produced here when you have a connection. So if the conductor is short circuited, AC current I will flow, causing the conductor to heat up. Okay, so when there's a short circuit, so we can see the uh, I1. So I1 uh, will be energized. Okay, and due to the short circuit, we can see the conductor will heat up. Okay, so if the second conductor is placed inside the first, okay, so this is the first. So we place more conductor inside, but it's not connected. So if the second conductor is inside, due to the electromagnetic field, the smaller voltage is induced. So so it will become like a wireless, so wireless charging. Okay, so it will charge by itself because of this electromagnetism. Okay, so similar it will goes inside and inside. So eddy current is a small current generated due to magnetic flux. Okay, so current can be generated using magnetic field. So that's why magnetic field is very powerful. Okay, so last slide for today. So the AC flux passes through a solid metal plate. So let's say AC current passes through inside. So in practical is equivalent to the densely packed set of rectangular conductor touching each other. So if we open this, so we can see so many rectangular conductor touching each other. Okay, currents go and path inside the plate, so the current pass through, and consequently, a metal plate that is penetrated by an AC flux can become very hot. So when you have a magnetic field and the current is passing through, so the material will become very hot because lower resistivity on the of the plate, because it's only having a continuous connectors attached to each other. So we can see the eddy current can be very less due to the lower resistivity. So, okay, so with this, so I have concluded part 2 for chapter 2. Okay, so thank you for listening. We will discuss further on this subtopic. So thank you.